Let's start going into the catenary structures, um, um, both in terms of frames and shell. Okay. Uh, of course, the things that we are going to discuss from now on can be applied to whatever frame or shell that you might want to consider. In this case, we are optimizing the structure in terms of performance so that it will be made up only of, it will be a compression structure, basically. Okay? So in order to create this kind of system, I'm going to use Kangaroo. This first block of this definition is actually Kangaroo creating the catenary shape. Okay, it's nothing more than that. I'm going to do this from scratch as always, so you will get all the steps and the details. So yes, basically, in order to create a catenary structure in Kangaroo, you can. I will be working with Kangaroo 2, not Kangaroo 099. You can simply create a mesh and use the mesh in order to derive both the frame structure and the shell structure. So everything will start with a mesh component. Now, you might know that Rhino is not exactly a mesh modeler. So when you want to model a controlled mesh, you might run into some troubles. Actually, Grasshopper adds some mesh modeling and editing capabilities to Rhino, but in the end, we are not even close to a polygonal modeler. So the easiest thing that you can do in order to define the general mesh that you want to use in your simulation is draw the mesh in Rhino using mesh primitives. Now, in our case, a catenary dome is obtained by deforming basically a planar mesh, which is subject to gravity. So I'm going to use some commands here like mesh, and I'm going to use polygon mesh primitives, and I'm going to start not with a plane because it already creates some complex mesh normally. I will create a mesh by face, so a 3D face initially. Now, just two observations. Since Rhino 6, anagons, which are basically polygons with more than 4 sides, are allowed. So you can click in more than 4 vertices, and Rhino can create a mesh polygon with exactly the same amount of vertices as the number of clicks that you did. Don't do that. Don't use anagons in your mesh modeling processes. Not even if you are working with a polygonal modeler, okay? Because they generate several types of problems. Okay, so I do recommend that you stick to triangles or quads, and eventually, in our case, we will be working with quads. So when you create a 3D face, the other observation is that always create a 3D face counterclockwise. So if you start clicking vertices from here, don't click the second, third, and fourth like clockwise. You always obtain a quad, of course, but the thing is that if you draw the vertices clockwise, you will have the mesh oriented downwards. So I will be working, for example, in perspective viewport. So if I create a 3D face like clockwise like this, and I switch to shaded mode, you see that my polygon is actually displayed as orange. If I go down, I see that the actual polygon is white. Okay, so orange is the color for my back faces in Rhino. I do recommend that you do this when you work with meshes. I do recommend that you go into whatever viewport you might want to use, like in this case, the perspective viewport, switch to shaded, and then go into display options. And here, display option opens up in the view display modes shaded tab. And here you will find that here, more or less at half the screen, you will see that there is a parameter which is called backface settings. I do recommend that you switch it from use front face settings, which is the normal standard value, to single color for all back faces. And you specify the color that you want to display for the back faces. Don't use a primary color or one of the standard color, because in that case you are not able to understand if you are looking at the positive or negative face. Use a color that normally you wouldn't use in a normal visualization. And from that moment on, your Rhino, whenever you open a file, whatever file, and you switch to shaded viewport and you are displaying a mesh object or even a Nurbs object, the negative face will be displayed like orange in my case. So if I go back to my 3D face, if I draw the 3D face like clockwise, I see the negative face. If I draw it counterclockwise, I see the positive face pointing upward. Okay, so pay attention to this detail, because well, it's important when it affects many things, as we will discuss in a while. Can we give a different color to preview naked edges? Yes, actually you can. So if I have this thing and I explode it and I delete one face and I join all the rest, we have interior edges and naked edges here at the top. This is something that you normally do when you run an analysis command like show edges. So in this case, you automatically see where are the naked edges. Okay, so this is what you can do in order to detect the naked edges. But in our case, I'm going to draw here a mesh by 3D faces. So first phase is going to be something. Remember that we are working in meters. Okay, so I'm going to create one first span like 10 meters more or less. Oh, also we can also grid snap, so things are going to come up more regular. So I'm going to create a 10 by 10 first 3D face counterclockwise. Then I do recommend that you activate the vertex snap in order to create another 3D face snapped to the existing vertices, and another 10 by 10 span for this mesh. And I'm going to create another one, and another one here, like this. You can create as many as you want. Of course, the problem in this case would be the limitation of the free version of Caramba 3D. So remember that if you are not running a full license, there will be some limitations. So the more you add elements to this, the more elements you will have in your simulation, and eventually Caramba will not be able to calculate everything. So in my case, just to make it a little more complex, I'm going to create another part like here. So I have created basically 6 polygons in this case. They are all separated polygons, even if they touch each other along one edge. So we must select all of them and join them together. And so now we have one single mesh made up of 6 quads. And this is the mesh that I'm going to import inside Grasshopper. So right click on this, set one mesh, and here it is. I'm going also to internalize this. There is, well, before internalizing this, yeah, we can internalize it and see if everything goes as perfect. Remember that Rhino is not a mesh modeler, so working with meshes sometimes can be very tricky, okay? So now we have created 6 polygons and joined them together with a join command. Now this join command is not typical from mesh modeling. It's a join command that works with lines, with surfaces, whatever, with polysurfaces also, okay? So it's not a dedicated mesh command. Now, joining meshes is not like joining surfaces or joining lines, okay? Many bad things can happen. So if I do this and I say, okay, I have one mesh with 24 vertices and 6 faces right now. So I do expect this mesh to work like one single mesh with these features, but this is not necessary so. So In order to create a workflow which is the more error-free as possible, to the maximum of our possibilities, what I would suggest is don't join the polygons here in Rhino. Okay, import these meshes, set multiple meshes, and import them separately here in, well, let's do this with some border. So set multiple meshes and select this. And join the meshes inside a Grasshopper. Grasshopper adds more mesh modeling capabilities to Rhino. Okay, so I'm going to internalize the separated meshes, so 6 polygons, and get rid of them. In Grasshopper, you can join meshes with the mesh join. Mesh join allows joining several meshes together. The only condition is that there must be some shared interior edge in order to perform this join operation. But there is another command that follows, which is called weld meshes. This is something that you must use, because in polygonal modeling, when you join one mesh face with another one, you might get duplicated vertices and therefore duplicated edges. This means that you might see an internal edge that will be exterior for one polygon and the other polygon. And so Grasshopper would not be capable of detecting that you have a border outside and some interior edges on the inside, and consider these, for example, like an exterior edge. You don't want that. So in this case, we get the same result. If you take a look at this, you always get a mesh with, you have 14 vertices and 6 faces. So you see that the number of vertices is significantly less than before. This is the actual mesh that we need to work with. Okay. Now, this is something that you might also do in Rhino, because there are some mesh tools that you can use. But I do recommend that you perform your mesh operations inside Grasshopper as much as possible. So here you will see that there is a weld mesh component or command. Okay, so this is what we are doing here. So once we have the mesh, what we're going to do is to, well, give it some physical properties in order for this mesh to deform according to gravity. Okay, and so we switch to Kangaroo directly. Well, first thing, this mesh actually has 14 vertices, 6 faces. We don't know how many edges it has. So I'm going to create a mesh edges component like this. And let's switch back to wireframe. So my curves are displayed with a higher thickness value, so they are visible. So we have 14 naked edges and 5 interior edges. Okay, so it's a total of 19 edges, which is suitable for a free version of Caramba 3D. The problem is that this object is extremely low resolution. Okay, so imagine that we are going to keep all these mesh objects anchored, for example, at the corners. So if you anchor all these corners here and you maintain this kind of very low resolution, this object will not be able of deforming at all, more or less. And so the problem is that in this case, we must increase the resolution of the object. Now, in order to do this, we can do a couple of things. The first one, the one that I prefer actually, is by using a Kangaroo 099 component. It's no longer present in Kangaroo 2. I don't know why, actually, but if you switch to Kangaroo 099, I'm assuming you have it installed. If not, I will show you a different process. In Kangaroo 099, there is a mesh group where you can find a quad divide. So quad divide is amazing because it takes all the quads inside your mesh and divides them using a number of divisions. So in this case, 5, you see that each quad is divided into 5 by 5 polygons. So if I, for example, create a slider between 1 and 5, 5 being already quite a huge amount of polygons for this simulation. So I'm going to define the number of subdivision that I want for these faces. And in this case, already we are dealing with 24 polygons. But the problem is that we already have something like 28 plus 34 is 62 edges total. So this is something that I can run in my Caramba 3D license, but you can. Of course, we are going to start with millipede. So with millipede, you have no limitations. Okay, so you can use this method if you want and increase the number of edges as much as you want in order to have a high resolution simulation. If you don't have Kangaroo 099 installed, you cannot use quad divide. Okay, so in this case, what you could do would be to use, for example, a Cutmore-Clark subdivision, which is from Weaverbird. Let me get rid of this preview. And the Cutmore-Clark subdivision not only subdivides the mesh, it only smoothens up the mesh. So if you don't want this smoothing to occur, you must select at least corner fixed or fixed at all. How does this work? Well, it doesn't allow specifying the number of divisions that you want along the sides of your actual polygons. Okay, but it's let's say loop, this kind of algorithm. So level is actually saying I take one quad and subdivide it once. Well, subdividing with a Cutmore-Clark algorithm means that you get 4 polygons out of 1. So the next iterations, you will get 4 polygons out of each polygon from the first iteration. So you don't have 3 by 3 quads. Okay, you will have eventually 8 by 8 quads, or sorry, 4 by 4 quads. Okay, so if I set this level with a slider between 1, 2, 3, it doesn't allow more than 3 repetitions because of the number of faces that you will create. So you see that with 2, you get 4 by 4, and then there is 3, and you already are 8 by 8. Okay, so you don't have this kind of direct control over the amount of polygons per side. Okay, this is a geometric progression basically. Or the other thing that you can do is this. Instead of starting with a mesh component or mesh object here, you could create, for example, Nurbs Surfaces like this. Oh, sorry, my bad. Like this. And then I'm going to copy this from here to here, here, here. Well, I'm going to get rid of this one. Like these Nurbs surfaces here, import them in in Grasshopper. So they're here. Let's internalize them so we can delete them. And use in Grasshopper, use the mesh surface component. And with mesh surface component, you take each of these plane surfaces here and decide, when converting it into mesh, decide how many polygons you want in the U and V sides, in the U and V direction. So if I take a slider between 1 and 5 and plug it both into U and V, I can play with the topology of this mesh a little more because I have the same control as the quad divide. Okay. So this is exactly the same as using the quad divide command. You see, we have exactly the same mesh result. But whatever method you are going to use, it doesn't matter. In the end, the important thing is that you come up with this kind of initial geometry. Okay. So we are going to start with millipede. Sorry, we are going to first of all simulate the catenary structure in Kangaroo, and then we will switch to millipede. So there is no limitation at this moment for as regards the resolution that you are going to use. Well, I can also use a single slider here, so it will affect both of our methods. So once you have this original mesh, we will use this inside Kangaroo. So let's go into Kangaroo 2. The first thing that you might want to do in a Kangaroo simulation is give your mesh or your elements elastic properties. So elastic properties is the property that keeps all the elements of the system together. Okay, it avoids the system to explode, basically. So it depends on how you want to proceed. In this case, for example, I don't care about extracting the edges. This was just to double check that the amount of edges was suitable for a Caramba 3D license, but it's not necessary at the moment. So what I'm going to do, I'm going to give elastic properties to this mesh. So I'm going into Goals Mesh, edge length, which sets the elastic behavior of this initial mesh. And one observation, remember that we are simulating with Kangaroo a structure that is going to be built in the real world. So even if Kangaroo only allows simulating elastic bodies, well, actually there is a rigid bodies in section in Kangaroo as well, but it's not suitable for this kind of simulation. Okay, so we are not going to discuss this. But if you are thinking about this as a rigid dome, a rigid structure, in terms of elastic behavior, it means that the length factor is going to be 1. So the elements of this mesh, they don't want to stretch or compress, basically. So their elastic behavior is relatively visible. This means that length factor must be set to 1, and that the strength, the elastic strength, is quite high. In order for you to have an idea of what kind of strength you must use if you want to simulate some kind of rigid body, strength can range from very high values like 10,000 to extremely high values like 200,000, 300,000, depending on the material that you want to simulate. So if you want to simulate iron, for example, or steel or whatever, we are considering the strength to be something around 200,000. The problem is that if you do this in Kangaroo, you will get an extremely slow simulation. And when I say extremely slow, it means that I can start running the simulation right now and eventually get to a final result or a converged system by tonight, eventually, I'm not sure. So I would recommend that you use Kangaroo only to get a proportional result. Proportional result means that you have the correct physical behavior, but eventually not the exact dimensional result that you are looking for. So in order to avoid extremely stretchy behaviors, I would say that strength can be increased up to, I don't know, something like 11 eventually, which will maintain the simulation quite fast, and yet it will be considering some kind of less elastic system. Next thing that we want to apply is gravity. Now, of course, gravity will make this object fall down. We want this object to fall up. Okay. So fortunately, we're working with a computer simulation. So if you go into Goals Mesh, there is one component which is called Vertex Loads. So in Kangaroo, gravity or loads are applied at the intersection of the edges. You just provide the mesh where you want to apply these loads and define the strength. The strength is a number because it's vertex load apply always a vertical load. Okay, so there is no need to specify with a vector what's the orientation of the load. You only provide a value. And the value is negative for loads that are oriented vertically downward, and positive if you want the load to be oriented like vertically but upward. In our case, I would suggest we start with some kind of 10 value and eventually tweak the parameters once we start seeing the result. Eventually, we are going to reduce this value here. Remember that if you want to work with real gravity in Kangaroo, like 9.81 something, you must also provide realistic strength to the material. And therefore, the simulation is going to be extremely slow. So I don't recommend you do this right now. So we have the system, the loads, and we miss the anchor points. And as for the anchor points, I'm going to mesh utilities here and extract the mesh corners component. So I'm going to take the mesh and extract its corners. Now, corner in Kangaroo has a particular meaning. It doesn't mean exactly the corners that you are seeing right now. Corner depends on the angle that you want to consider. Okay? And the angle is expressed in radians, as always in Grasshopper. So remember that 180 degree is 3.14 in radians, and 90 degree is actually 1.70 something in radians. So we are considering an angle that's higher than 90 degree but lower than 180 degree. So if you change the shape of this mesh or initial mesh object, even if you don't have 90 degree corners and you have wider angles, eventually they will be detected as corners as well. So that's the meaning of angle. If you increase the angle, for example, to be extremely open wide, then you can also consider these as a corner, for example. And so anchor the mesh all along the boundary. But anyway, we can stick with this first result here. So we have everything, basically. We have all the constraints, load, and the system. So we can run the simulation. I prefer to adopt the entwine method when creating a Kangaroo simulation. So I take an entwine, I plug in the first branch the result that I want to have available after the simulation as first option. And in this case, it's not the edge length, because the edge length is actually giving elastic properties to the edges of the mesh. I want the mesh to be my primary output. And so I grab a show component and plug the mesh to this show component. This is doing nothing. It is actually not a force, nor a constraint, nor nothing. It's just telling Kangaroo that I want to see the mesh during the simulation. Okay? And so I plug this mesh in branch 0, 0. Edge length, I plug it into branch 0, 1. Because edge length is another goal, another force that has some geometric preview. So you will see lines displayed during the simulation. Vertex loads is a force actually, and corners are constraints. They don't have a geometric preview. So I plug all of them inside branch 0, 2. So this is all the goals that I want to have inside my simulation, my Kangaroo simulation. First of all, I'm going to stop Kangaroo from running by plugging a Boolean toggle false to the on input. And I'm going to create a button here to reset the simulation eventually. And so I have these 3 components here, and I'm going to plug the goals to goal objects. There is an error here. Oh, I think I made a mistake, because this is actually detecting the points, but it's not a Kangaroo goal. So I must specify that these are going to be anchor points. So goals point, anchor, and this is going to be the anchor point. So that was my mistake. So I'm going to detach this wire and attach this other one. Yeah, now it works. Normally, I do recommend that you turn off everything that's on the left of Kangaroo in order to concentrate on the actual preview. And I don't want to deal with the edges or the vertices and so on. I just want to see the final aspect of our mesh. So the mesh was plugged inside the first branch. So it's going to be the first available outcome of the simulation. You see that the first value is a mesh. So even if you provide a data tree here, the output will always be a list. So in order to work only with the mesh, we need to extract the mesh from this list of values. The smarter way to do this, even if the mesh is going to be the first of this list, we could simply use a list item. I think we all agree about this. So the list item with index 0 is going to be exactly the first value, which is the mesh. Okay. But as we are using the entwine method, it's smarter to do something like this, to take a partition list component, to explode the actual tree, and also to use a tree statistics. So what I'm doing here is this. I'm extracting the features of the original data tree. Let's place it here. So I know what's the length of each branch of this data tree. 162.49. Okay. So if I take the list of outputs of Kangaroo and partition this list using exactly this length, what I get as a result is another data tree with exactly the same structure as the original one, but this time I have the content is going to be the deformed geometry. So if I explode this data tree here, I will have the branch 0 contains exactly the mesh. Branch 0001 contains what is connected to branch 01, which are the edges of the mesh. So they are already separated, like here, and deformed. So that's why I plugged the goals that have some geometric output as in the first places here. And then all the goals that don't have a geometric output, they can be merged together into one single branch. It doesn't matter, actually, because you are not going to use them. With this method, you can extract exactly the information that you have plugged in the initial system from the correspondent position. So branch 0, branch 01, and so on. I only need, for now, the mesh, so I'm going to concentrate on the 0000. So this is the mesh, and if we run the simulation right now, we see this. An extremely low resolution system, but this is already a catenary structure. Eventually, due to the extremely low resolution, we could have some weird behavior in these areas. Okay, as we are going to work with millipede, what I suggest is in this phase, we take the original system and increase the amount of subdivisions to 4x4 at least. So we have a more catenary style behavior. This deformation here is something that depends on the elasticity of our system. So this is just visual. You cannot have any control unless you use real life parameters here, and unless you're keen to wait hours for the simulation to find an equilibrium configuration. Okay? So I do suggest that you don't increase this too much. We are in a range up to 100 right now. So if I increase it to 100, we already have more elastic resistance to the deformation, and we get a more, let's say, balanced aspect for our system. So the other thing could be to decrease the strength of the vertex loads, so basically gravity. Okay, but nevertheless, this structure is always a catenary structure because it is only deformed by gravity. Okay. So we are getting a structure that, if you take a look at this from the right viewport, it is the lowest points lie at 2 point something meters. So it's something that relates quite well with the human scale. So you can like move below this dome in whatever part. And also from the front viewport, you see that it's more or less the same height. So yeah, let's say that this is what we are going to analyze in our optimization process. In order to avoid any risk of connecting a complex part like the optimization process, which requires some calculation, to this initial part, which is almost interactive, as you can see, I do suggest that you do something like this. First of all, you switch to false. So once you see that the solver says converged, you can switch to false this toggle. So this is no longer calculating, and the final configuration stays like fixed. don't push the button here, because that's you're going to reset the mesh to its original state. And once you do this, in order to separate this result from the next step, I would use a data dam. So this mesh here is actually passed to the second part of the definition only when you press play. So here you see that the output is empty, but if I press play, now the output says mesh with whatever information. If I change something here in the simulation, like reset it, for example, I see that this mesh gets reset, but if I plug a mesh here, I still have the, oh yeah, actually, this is weird. This should not happen, actually. This should not be happening because the data dam should separate this step from the previous one. This is absolutely something that I don't understand actually why this is happening. This should not be happening, guys. So it's very strange. I wasn't expecting to see this, but anyway, if this doesn't work, at least I do recommend that you do something like this. You pass the actual mesh to a mesh container and internalize this value. Okay, so whatever operation you do on the initial simulation with Kangaroo, you don't have it applied to this object. Okay, so you always have the last version of your deformed object, of your catenary structure, stored inside this component. Okay. This also has another effect that if you, for example, forget to switch this to off and you save the file and everything is connected to the optimization process, this, once you reopen the file, this starts to calculate the deformation, and each step of each iteration will be passed to the optimization process or structural analysis processes. And so you will have a real-time calculation of a changing structure, which is something that you don't want to happen. Okay. So basically, this is the first block of our definition, which is the catenary structure creation. And now let's switch to our analysis. And I'm going to use millipede at first. So in this case, you could also use the FE mesh, for example, but you are going to create a shell element. We are going to concentrate on frame at first. So frame curves, for example, frame curves is capable of considering all the curves at once and apply one cross section to all of them and one linear load to all of them, and eventually also anchor them somehow. I don't recommend you use this unless you are working with an extremely homogeneous system. Okay, and also as we want to run some optimization process, I do recommend you stick to the previous workflow, which was to use the FE frame element. So we have the mesh. We can use the mesh edges component, which is something that eventually you can avoid if you want, because you can also use the 001 branch, which contains actually the deformed edges. So you already have this value here. You can also create a line container, pass these edges to this line container here, and internalize these values. Okay, so you can avoid this mesh edges extraction. So we have the lines. We can take the endpoints of these. Remember the process to graft these and to graft these. I'm not going to explain everything right now, but if you have doubts, you can always interrupt and ask. So these are actually the connections. Now we need the cross section. Cross section, let's say we are going to use, well, simple circular hollow cross section like this one, and I'm going to use material like steel. I don't want to waste time with this. And inner radius and thickness. Now, in this case, I need to parameterize them because I want this to be a parameter for our multi-objective optimization. So inner radius is going to be a gene pool. Remember that gene pool amount of sliders must be set according to the amount of elements that you are going to calculate. Okay, so in this case, in my case, it's 220. I do recommend that you do this if you are going to work with this kind of procedures. I do recommend that you do something like this, like list length this with a flatten, because you don't know from where you are getting the lines. Normally, that it could be also a data tree, so you must know how many elements you have, and you create a panel where you can see exactly the amount of edges that you are considering. So once you do this, you place it close to your gene pool, so you know how many genes you need. 220. Now, if you try, for example, to use 1,100 elements, you see that everything works. If I try to use 2,000 elements, it sticks to 1,000. 1,001, 1,000. So this is the maximum amount of sliders that you can have inside the gene pool. Okay. So if you need more than 1,000, you can use two gene pools. Remember that they output a list of values. So if you merge two lists, you will have one single list of more than 1,000 values. Okay. So this is going to be our 220 genes gene pool. Decimal values, this is the inner radius. We are working in meters, so we are going to say we want 3 decimal numbers, and the inner radius is going to start from let's say 25 millimeters, like 5 centimeters radius, and maximum of 0.05 millimeters, sorry, meters in this case, so 5 centimeters. So this is the thicker bar that we are going to obtain. And to this we must add the thickness. So I'm going to do this right now. So we need as many thickness values as the radius. So I'm going to duplicate this gene pool, plug it into thickness, and in this case I'm going to use something like 0, let's say we give this like 5 millimeters up to, by the way, I think that you see we are not able to specify the third decimal value in this case, and eventually, let me double check, but it might be because we are using a absolute tolerance of this entity here. No, it simply doesn't allow to do this. This can be a problem. This is the first time that I see this, but I wanted to give a thickness of let's say 0.005 millimeters. Yeah, this is the first thing that I wanted, and eventually 0.02 centimeters, like maximum thickness. I think that I think I did it in the wrong slider. This is strange because I see the sliders here with 3 decimal values, but I don't see them in the actual gene pool parameters. I also switched the gene pool, so I'm going back to the actual correct configuration. So let me double check if I can see. I missed this also here. So let's see if I create another gene pool. At least I need the possibility to tweak up to the third decimal. So we need 220, and then now we have 3 decimals here. I don't know, in the copy, it's like when I copy the gene pool, It doesn't display all the decimal numbers. I don't know why. So this is something that I should report to McNeil eventually. And the maximum thickness, I said it was something like 2 centimeters. Yes, exactly. Okay, so perfect. And this is going to be the thickness. And I'm working with all these elements at once, so I don't want to differentiate the different portions because there is no reason to do this. And cross section, I'm also going to graph the cross section so that it's going to be applied one cross section per element. And now there is the linear load, and the linear load is going to be z vector with a factor of minus x, sorry, Spanish, English, and a slider of 101. So we have quite a nice range of loads that we can apply to this thing. Linear load is, you see that here is Newton per meter. Okay. So pay attention to this. Actually, this is just for testing the system. You can also apply real life values to these parameters. And the up vector. Now, the up vector here is 0, 0, 1, which is not exactly correct. As you know, the up vector should be perpendicular to the orientation of the beam or of the element. And we saw this yesterday, so we must take a, actually, we can take directly a perpendicular frame for these curves. And I'm going to reparameterize this curve and use 0.5 as the parameter. So this will give us the perpendicular frame at the midpoint of our elements. And we can use, for example, the x-axis. As you can see, the x-axis is more or less always oriented downwards. So we can deconstruct, oh, there are too many plugins. This is the result, deconstruct plane. And so the orientation for our the up vector for our elements is going to be the x-axis. Now, this is something that that in our case is totally. My bad. You saw the time that it took to perform this simple operation. This is because I didn't graph the up vector. So you see that we are getting 220 branches, each one containing 220 elements. This is not correct. We only need 220. This is because I didn't graph the up vector. So pay attention to this. Now I was fortunate because was lucky because it's a very simple operation. But when you have a very complex system, this can crash Grasshopper. So now it's correct. One branch, one beam. Now in this case, for this kind of structure, this up vector definition is like considering a very detailed feature of the structure. But as we are working with a symmetrical cross section, we could also stick with the up vector like 0, 0, 1, like the z up vector. Okay, it doesn't change almost anything. But it's better to have the cross section oriented like perpendicularly to the element. And okay, that's it. Basically, we have the frame elements. Let me hide all of these things. Next, for example, support. So FE point support and support type. I'm going to anchor this structure like, let's see, these are all set to true, so we have a fixed support, and I want to anchor the structure at, well, of course, the point that lie here at the bottom, on the ground. So we already have those points. They are the corners. So we can grab a point container and pass these points to this container, make it wireless. in order to avoid long cables, long wires inside our definition, and plug these points here. So we have also the support. Load is already defined. If you want to add additional loads, actually you could do this, but I do not recommend you do this. We are working with a catenary structure in this case. So let's stick to the Kangaroo simulation. Even if it is proportional to real life, now we are going to find the proper thickness and performance of each element in order for this catenary structure to basically uh, stay in place, right? If you apply an additional load to this structure in a specific point, you should do this starting from the Kangaroo simulation, okay? Because if you do this only in the structural analysis, you will have only the correspondent element will react to that additional load. So you will have always a catenary shape, of course, but it's like there is some discrepancy between the way that you create the catenary shape and the way that you make the catenary shape work in a real condition. So I would suggest that you add the load in Kangaroo and then consider it also in Caramba or in Millipede in this case. Okay? But it's basically just semantics. You can also do this directly in Millipede or Caramba 3D. So I think this is pretty it. So let's build the model. So FE system, the elements, and the supports. That's it, because we don't have any other loads. Let's also turn off the preview of the original geometry, and let's simulate this structure. You see that we are considering a linear load, but you can also use a self-weight coefficient here, which is by default set to 1. And then we have the FE model. And this FE model, we want to show the frame visualization in order to see what happens to these things. So now we want to switch to, for example, well, actually, for now, let's stick to the mesh representation. So everything here is now perfectly homogeneous, but one single beam. We could also easily find it because it's the thinner one. I suppose it's somehow in this area because this was the first polygon. But anyway, we already have this kind of control over the system. Now, let's try and optimize it in order to see what result we get. So I'm going to take the max deflection and weight as always. We can also, in this case, copy all of this, copy paste it, and bring it here. So we have mass, which is basically weight, and max displacement, which is basically max deflection. Okay, here we are. Okay, you see that we have 8.2 meters maximum deflection for our structure. So yeah, it's quite a deflection. The deflection by default in the frame visualization is set to 0, so you don't see that deflection. If you plug max deflection to deflection directly like this, you have this kind of weird result because this is actually like a percentage. It's not exactly like in Caramba 3D. Okay, so it's absolutely nonsense to do this. That's why if I prefer to make this kind of very simple operation here in order to create a proportional display of the deflection, but in a more controlled way. So this is something that we did yesterday. I'm not going to focus on this, but I want to point out what is the behavior of this. So you see that this is the actual deformation that we are going to obtain. So let's take goldfish. These are the objectives, and as regards the parameters, I'm going to use just the thickness and the inner radius as parameters, just these. So let's optimize this thing. You will eventually see that these beams of these elements are going to change randomly their thickness. So let's reset and start. Yes, you see it's totally random. I will leave this. You see that it's quite slower than the previous one. It has much more elements right now. I'm going to show you just, in this case, I think I have some images of this. Maybe here. Yeah, this one, for example. Um, this is already a process with 63 iterations. See the cloud has become very dense. You see these dots here are overlapping, but they are a huge amount of points. And here you see what's the final result of this simulation. The mesh, of course, is different from the actual one that we're using, but this is the actual result. It's not visible here in terms of thicknesses, but you might recognize that these elements here are thicker than the upper elements here at the top, of course. Okay, so this is the result that we expect to obtain from this optimization process. So at first, of course, you will have the thickness would be randomly distributed, but as long as you leave this running, you will get to a much more refined result, which tends to have thicker elements at the bottom and thinner elements on top of these dots, of course. Now, this is the maximum deflection. It's still quite high, as you can see. So it's better here to leave this running. And I do recommend also that in this kind of structure, eventually, well, it depends on what type of compromise you want to obtain, but probably the maximum deflection is a little bit more important than the actual mass of the structure. As this is a catenary structure, it's going to work basically more or less no matter what. So maybe it's better to concentrate on having less deformation than a lighter structure. But this is basically depends on many factors. So it's just a generic observation in this case. So you see that we already dropped to 5.5. We can pause this and reinstate this in order to have a look at what happens. I think we're still far from the final solution, but we already see some thicknesses here concentrated at the bottom of the structure. But anyway, this is something that you might want to easily run. Now, one thing that I also put in this course, in this program, is that this kind of structure is very nice, actually. There is one little problem here, which is production. So say that you want to build this thing, actually, and not as a frame. The frame is easy, actually. So you can also, for example, once you have the general shape of this thing, you can also create. Well, not only you have exactly the dimension of the elements that form this shape, so you can cut these elements with the proper size in production. But you can also work with the joints. So each joint here is basically a custom shape. So you must produce a huge amount of joints, different joints. But it's easy to obtain the shape because you are working with a parametric tool. So you just, let's say, I don't know, the simpler thing that comes to my mind in this case would be to, sorry, grabbing the pen. would be to create some kind of joint like this with some elements, you know, and it's going to be a four-way joints here. It's going to be a three-way joints in this along the naked edges and so on, right? And eventually two-way joints in the corners. But this is easy because these elements are going to adapt with according to the deformation that you get from Kangaroo. And you have these parts here that you can simply extract and eventually do whatever you want, from 3D printing to casting to whatever you want, or assembling if you want. But so you have all the information because you have the angles and everything. Okay. So this is something that it is not worrying. But the thing is, what if you want to place panels and close these areas between the frame elements? So in this case, the main problem that we have is that even if we have quad panels here, they are never planar panels. In order to have planar quad panels, the four vertices must lie on the same plane, but this is not the case. I think not even one of these panels is perfectly planar. So the easiest thing that you can do eventually is starting from this deformed mesh. You can see that there is some distortion inside one panel. You see there's light and shadow inside the same quad panel. So the easiest thing that you can do is triangulate it. So if you triangulate the panels, you will get this representation here. So you have a triangular panel inside one quad frame. And of course, this mesh here is only made up of a triangle. So faces 192 instead of 96, of course, it's double the amount of faces. If you mesh explode this, we now have separated triangle. So you see that we have 192 meshes, each one having 3 vertices and 1 face. So they are triangles. And you can take them and eventually also lie them flat on the ground plane, on the XY plane, in order to prepare them for some cutting technology like water jet cutting or whatever. Okay, so this is the easiest thing. But there is also another thing that other things that I want to give you as alternative, which are, I wouldn't say more complex. At least the first one is not more complex. You can ask Kangaroo to consider planarity during the simulation. So in Gold's mesh, there is one thing that is called Planarize. Now, I don't recommend you play too hard with this Planarize component because it has an undesired effect. So of course you can take the mesh and tell Kangaroo, please keep the quads planar with a specific strength. Okay. The problem is that by keeping the quads planar, you alter the shape of the catenary structure. So it is not going to be a catenary structure anymore. So if you exaggerate with this thing in order to get perfectly planar quads, it's certain that you can manufacture these planar quads with a cut technology without having to do nothing here, like triangulation or whatever. But you are compromising the stability of the structure at the same time. So I wouldn't exaggerate with this component here. And the other thing that you can do eventually, if you don't want to, but because the problem with triangulation is that, of course, you get flat planar panels, but you get double the amount of panels. So you must do double effort to assemble this whole structure. So if you don't want to triangulate your structure, there is an alternative that I can suggest, which is called Ivy. Now, we are not going to analyze Ivy in detail because it's somehow very tricky to come up with a perfect result. I think, if I am not wrong, because this is one of the first things that I was doing, I think, yes, this is Ivy in action. I'm just going through the main behavior of Ivy. Let me just copy paste this block here so we can apply it to our new script, which is this one. Let me move everything down. Okay, so let's activate these and let's pass our mesh to Ivy. Okay, so let's pass this to here. Okay, first thing that Ivy does in this case, well, I asked Ivy to do, is not stripper nor triangulate. These are both. These are all component control alt stripper. This is from Kangaroo actually. It's a mesh utility. Triangulate is pure standard Grasshopper component, and then graph from mesh. Now this is Ivy, okay, from here. Now, in general, what does Ivy on a mesh? It determines a connection scheme between the faces of a mesh according to some geometric properties. In this case, I'm using face angle edge weight. So this component is determining a connectivity scheme based on the angle between two adjacent faces. Now, the first operation that I did was creating stripes along this mesh. Because if I don't do this, the original mesh is a non-directional mesh. So if I apply this method to the original mesh, like for example, like let's take these two here and plug them to the mesh. If I do this and take a look at the connectivity graph of this, you will see that, well, actually, there is some weighting that we have. This weight is heavier because the angle is narrower from between these two faces. So in this case, the connectivity scheme is not that clear, and therefore the unroll of the mesh is not going to be, let's say, we are not going to avoid overlapping faces, which is the main goal that we want to achieve. Okay. While if we first create strips along this mesh, now we can unroll the strips. Okay, so in this case, for example, if I take a look at the mesh graph visual unroll, okay, which is this one, if we increase the coefficient of this, you will see that these stripes are going to flatten, each one in its with its orientation. This is not a problem actually. But we are capable right now to obtain an optimization of the cuts in production. Okay, we can reorient these meshes actually and lay them flat on the XY plane. But anyway, this is something that I will leave this in the definition, so you will be able to at least start playing with Ivy. It's a very powerful tool. I absolutely do recommend that you play with it and understand how it works. It requires some further investigation on some algorithm. For example, the primary segmentation, which is probably one of the most complex feature of Ivy. But it's worth if you're going to produce this kind of complex structures. Okay, so it gives you some very nice and optimized workflow in terms of production. Let's go back to our stuff. So these are the main three alternatives. So triangulation, of course, I was striping the mesh and then triangulated, but I can also avoid triangulating the mesh. Okay. So triangulation, Ivy, and Planarize during the Kangaroo simulation. Okay. So basically, with this, I think that we can also produce this kind of complex structure. And let me go back to this, because there is another thing that I want to point out. Let me also Control G, Control E, all of this. And the only thing that I need in order for this definition to work, you see that many components are orange because they miss the original mesh. So I'm just going to take this original mesh here, which was the welded one, and the quad divide. So I'm going to plug this here, let me also reactivate this so I can internalize this value and use it for the previous definition. So you will see what happens here inside of this script. In this script that I'm going to share, of course, with you, I also put some indications, as you can see. So working with the original mesh, which is not going to be the one that I'm using right now, if you set the dimensions to 1, you will be able to use a free Caramba license. If you set it to 2 or 3, you will need a full Caramba license. So actually, I think I made a mistake here because I'm getting a very high resolution mesh in this case. So I think that, yeah, I think that I should use only the wet mesh result. Yes, and not the odd divide. So yes, like this, internalize data, Control E, and let's go back to our script. Okay. So yes, this is subdividing. Now everything is working here inside. And what I wanted to show you is also this. This is the actual. Well, I didn't touch anything inside this definition. So I suppose that these genes are actually set to the optimized version of the frame structure. So I just have to take these two things here, Control E, activate the result of Kangaroo simulation, and run the simulation again. Oh, no, because they refer to the previous mesh. Yeah, no, I cannot use the new mesh because I have to adjust all the gene pools and so on. So I cannot do this right now. So the only thing that I can do is open the Catenary Structure optimization file, which contains exactly this mesh here, which is going to turn gray in a while. Yes, exactly. And I absolutely need to work with this, and not with this one. I cannot use this one, so I need to go back to this mesh. And I can also hide everything and go back to this, and now I can run the simulation with the proper mesh, which is this one. Oh, I also added an anchor point here at the center of this structure, so I have this kind of falling down at the center of the catenary structure itself. Okay, so as soon as you see converge, but actually, even if you don't see converge, but you see that the system is not changing anymore, it means that more or less you are already reaching the equilibrium status. So it's up to you. This is a precise solution, but if you stop it once you don't see any changes in the model, then I think it's good enough. And reactivate these two things here. So I have 145 lines and 145 genes, so I think we are pretty good with this. And eventually we should have some nice diagrams here. And this is another result analysis. These are the node results, where you have location of the nodes, of course, and displacement. So this is the, let's say, individual displacement for each of the nodes of the structures. Okay, and in this case, for example, I'm using this displacement, which is basically, you see that there are 3 values here. When you see 0, 0, 0, is because you are seeing an anchor point, of course. But these are 3 components, the 3 special components of the displacement vector. Okay, so I take the length of the vector, which is the amount of displacement that you have per node, and then remap it and do something in order to visually see what are the nodes or the part of this mesh where you get the highest deflection, basically, or deformation. Okay, so these are the areas inside this mesh. And here there is also some let's say visual representation of these values if you want. You can do whatever you want with Grasshopper once you have the results of the simulation. Here there is also Opossum. Just to give it a quick look, once and forever, it's totally different. Oh, I think I have to replace the license here. But anyway, the interface is totally different from Goldfish. I will do this, so tomorrow we will be able to see Opossum interface as well. There is another preview here, which is these. What are these numbers? Sorry, I don't remember. Oh, I think it's just the thickness of the beams. But anyway, this is actually the millipede Catenary framework optimization that I ran for this original system. Now, the actual simulation that I was running is a little different. It's a little more complex as regards the mesh. I will leave it running today after the course. So in the end, I will share the definition where the gene pools already have the optimized version of each element. Okay. And in order to complete this analysis, the second part is the Caramba 3D optimization and analysis. So once again, 145 and 44 values for our elements, 145 also, and 44, sorry, but also here. And you see that I have this gene pool, which is actually connected to the elements, to the real elements. So this one here is actually connected to also to this second part of this definition, because what I did here was also to create a different representation of our object. So just in order to give it a quick look, this is a volumetric representation of the structure, like with a single element, a single mesh, which is all seamlessly joined together by using this plugin, which is called Dendro. It's just giving thickness to object with a mesh representation that you can merge together in order to obtain one single mesh instead of separated elements. Okay. So that's why we have this kind of intricate things here. And also there is another part here which are just tagging and text. So I will not concentrate on this. I prefer to take a look at Caramba 3D. So millipede is already turned off. In yellow, you see the components that actually it's worth turning on as a preview because they have some geometrical meaning. And this is actually the beam view with the deflection actually showed up in pink. So displacement actually, so actual stress, utilization, which is in this case, well, all the elements are in use more or less. Cross section is actually the standard mesh representation. Also, one thing to pay attention is that even in this case, in the line to beam conversion, I specified that in this case, I want the beams to have bending stiffness. So this is not a truss. Okay, so these beams can eventually also bend. Okay, so it's a little more complex than a simple truss. So here you have also the analysis, for example, of your components. Of course, this is a catenary structure. It's a compression structure, so you only have bluish normal stress inside these elements. There is no red, of course. So everything works as expected. Yes, and here we have some optimized cross-section display, because I also gave you here the workflow for creating, let's see if it's just this. Yeah, it's this one, for creating this, which is basically the catalog of all the beams all the elements that we are using. Oh yeah, by the way, you see that in Caramba 3D, the cross section here is a square or rectangular hollow section. So that's why we have this preview and not the circular preview like in Millipede. But nevertheless, you can also create the same profile here and use the same gene pool if you want. In that case, you can also compare the solution from Millipede with the solution from Caramba 3D. So yeah, and the last thing that we have here already is, oh yeah, here I was trying to associate the cross section with the relative element it belongs. So you also have a let's say construction scheme where you easily can associate one profile to one specific position inside the structure. This is for assembly purposes, of course. So let's leave this off by default.